Okay, thank you very much. Maybe. Okay, so I will talk about non-holonomic constraints, and these are part of the picture that Alessandre showed you. But this is the vertical, the rolling disk, not the vertical rolling disk, the general rolling disk. So this is a ball rolling on a table. This is the Chaplin sledge. This is, as we call it, the Celtic stone. This is a device, very interesting device, which is a non-holonomic device. These two men are observing, this is, well, do you know the names of these important persons that are Wolfgang Pauli and Niels Bohr examining the tippy top. The tippy top is it's not a true non-holonomic device, because there are other kind of forces acting on the tippy top. There are some gyroscopic forces acting on the well, but this is an interesting picture, because there are two important men looking this device. And my talk, by the way, is a joint work with Juan Carlos Marrero, Asier López Gordon, and Manuel Lainz, some collaborators in La Laguna and in Madrid. But my talk is about two papers published in 1951 in Proceedings of the Royal Society. And these two papers were presented by, as you can see here, presented by Dirac. And this man, Eden, he was an important man in an important physicist in the United Kingdom. He was founder of more or less the nuclear physics in the United Kingdom. But this is part of his PhD thesis. In fact, the thesis consists in practically these two papers. And it's relevant to know the advisors of this thesis. This is Richard John Eden, and these are the two advisors, Dirac and Werner Heisenberg. So I think this is not usual to have a physicist in these subjects advised by these two important names as Dirac and Heisenberg, two Nobel Prizes. Anyway, two physics Nobel Prizes. The objective of these two papers was to study non-holonomic mechanical systems and to develop a quantization procedure for non-holonomic mechanical systems. So in the first paper, Eden treat the case of Hamiltonian dynamics of a non-holonomic system, and in the second paper develop the quantization of these systems. Just using this direct correspondence between observables and operators and Poisson brackets and commutator of operators. But the point is that to have to represent the dynamics with a bracket, you need a bracket adapted to the non-holonomic systems, because the canonical Poisson bracket on the cotangent bundle is not able to represent, to give the non-holonomic dynamics. So these two papers, even the relevance of the thesis was not practically ignored by the literature in the last 70 years. You go to citations in the people that work on non-holonomic mechanical systems, you don't find any citation to these two papers, and they are, in our opinion, were important papers, and we try to understand what Eden did in these two papers, because it's not easy to read the papers, because the papers are written in a local language. So we find a lot of local computations, and it's difficult to understand what is doing. So our first task was to understand the geometry behind these local expressions. And indeed there is an operator that he defines an operator using different matrices and some trees, and they finally define an operator that this operator we call gamma takes an state, unconstrained state, and if you apply gamma, you obtain a non-holonomic constraint. So this is the use of this operator gamma. When you start to study geometrically the problem, you discover that this is just an orthogonal projector. So it's very easy. So the first task was to identify this bracket in this non-holonomic, because indeed he don't define a bracket. He defines something like a bracket. But we can define a bracket using this operator gamma. But there were another brackets, another non-holonomic brackets in the literature. So what is the relation of all these brackets? So in this paper presented in GCI, we proved that all these brackets are the same essentially. So this is the main result. Let me start with a brief description. It's not the same description that used Alexander, because he used the D'Alembert principle, but I will use only differential geometry. So we have a Lagrangian function defined on the tangent bundle of the configuration space. We assume that the Lagrangian is regular. Indeed, we will assume that the Lagrangian is of kinetic types. This is the kinetic energy of some Riemannian metric minus some potential. And using the geometry of the tangent bundle, we can construct these two forms, lambda L and omega L. Omega L is symplectic because the Lagrangian is regular. And so we can obtain, we define the energy, the energy of the Lagrangian as the axiom minus the Lagrangian. This delta is the Liouville vector field in the tangent bundle, the vector field generated by who generates the dilations along the fibers. And so this EL is the energy, and the corresponding Hamiltonian vector field for this energy EL is just the Euler-Lagrange vector field, which is this vector field psi L, which in this case is a second-order differential equation. This means that this is a vector field on the tangent bundle, but with some particular properties. And if we compute, we calculate the integral cubes of this vector field psi L, and the solutions are the projections of the integral cubes, that the solutions are the solutions of the Euler-Lagrange equation. So this is a way to describe Lagrangian mechanics. And to recover the Hamiltonian description, you only have to use the Legendre transformation, transforming positions and velocities into positions and momenta. And so we can define the Hamiltonian H, and so you use the canonical symplectic form on the cotangent bundle, and so we obtain the Hamiltonian vector field, and the integral cubes are the solution of the Hamiltonian equations, and we can relate both sides using the Legendre transformation. So this is the usual thing in Lagrangian and Hamiltonian mechanics. On the other hand, we can define the bracket. The bracket on the cotangent bundle is the canonical bracket. Yes, is the bracket defined by the canonical symplectic form. Okay, so well, this is a Poisson bracket, and one of the main properties of this Poisson bracket is you can define the evolution of an observable just doing the Poisson bracket of the observable with the Hamiltonian. So this is. And these are the things that we are asking for a convenient bracket in the constraint in the non-holonomic case. Okay, so this is a non-holonomic mechanical systems, a manifold Q, a Riemannian metric G, a potential B, a non-holonomic distribution D. So we are considering only linear constraints, not non-linear constraints. And this is the Lagrangian. And these are using a geometrical tool you can obtain the equations of motions. Where this lambda A are Lagrange multipliers, this mu A are a local basis of the annihilator of the non-holonomic distribution D. And so we can write the equations in this equation 6 and 7 in this geometrical way. And so this equation has a unit solution, which is the Hamiltonian, the non-holonomic vector field, given the non-holonomic motion. Because we have a Riemannian metric, this metric permits to pass from vectors to covectors, just raising and lowering indices is the usual way, and we can define, using the Riemannian metric, the complement, the orthogonal complement of D, this D perp, just the orthogonal complement. And you have this Windy-Sand decomposition of the tangent bundle of Q in D plus the orthogonal complement of D. And we can pass to the cotangent bundle and do the same thing, because we have the metric on the tangent bundle, but we have also the metric acting on covectors. So we can do the same. This D is transformed by the Legendre transformation. The Legendre transformation is just the transformation given by the metric, nothing else, because it's just the partial derivative of the Lagrangian with respect to the velocities. So this is the components of the metric. So and so this M is just the image of the constraints of manifold D on T star Q. And now we have this other decomposition, which is very, very easy to show that we have this decomposition, because T star Q is a vector bundle. So this is a with-not sum of M, which is again a vector bundle, so a vector subbundle of T star Q. We are considering linear constraints plus the annihilator of D. And so just this some strain operator gamma defined by Eden is just the projection of T star Q from T star Q into M. This is the gamma. So this is you have the inclusion of M T star Q and the projection gamma from T star QM to M. And well, this is the Hamilton, the non-holonomic equations in the Hamiltonian side. Okay, and this is another way to define to write the non-holonomic equations. And again, we have a unit solution, which is the non-holonomic vector field, and both vector fields, the non-holonomic vector field on the tangent bundle and the on D and the non-holonomic vector field on M are related by the Legendre transformation. Okay. And but there is another description of non-holonomic systems using a generalization of Lie algebroids. This we will use this name skew symmetric algebroids, or sometimes almost Lie algebroids. So these are algebroids. The only different thing with a Lie algebroid is that they don't fulfill the Jacobi identity. The bracket don't possess this property, this integrability property. Indeed, the Lagrangian is defined on the tangent bundle, but we have this D. This has a structure of skew algebroid, because you have this decomposition of the tangent bundle of Q in D plus the orthogonal of D, and just to define the bracket in this skew symmetric algebra, you only take two vector fields, X and Y. The bracket is not in principle in D, because D is not integrable, it's the non-holonomic constraint. And but to get a better feel on D, we only need to project by this P. And so this is the Lie bracket in this skew symmetrically algebroid. And also, well, we have this the interest to deal with Lie algebroids or skew symmetrically algebroids is that everything is simple, because you consider adapted basis to all these vectors and bundles, and then the things are completely simple. So inclusions are inclusions, real inclusions, projections are projections, so everything is more simple. Okay, and we can define this bracket. This bracket is defined on D star. So our phase space now is D star, the dual of the non-holonomic vector bundle. And so this bracket has all the properties of a Poisson bracket except the integrability condition. Okay, and so one can prove that the dynamics is just the evolution of any observable is just given by the corresponding non-holonomic vector field and so on. So we have these two descriptions of non-holonomic mechanical systems, one on the tangent or cotangent bundles, and the other one on a skew Lie algebroid and the dual of the. Don't forget that there is a relation between skew symmetric Lie algebroids and linear Poisson structures on the dual of the Lie algebroid. So this is a very important relation in mathematical physics. Well, but there was another, a previous defined non-holonomic bracket, which is defined just considering that the tangent bundle of the tangent bundle or the cotangent bundle can be decomposed in two different ways to have a symplectic decomposition. A symplectic decomposition is important because it facilitates many operations, and this is one of this. We can consider this vectors bundle of Tm. This is just defined only along the constraints manifold M, and so these are the tangent vectors that the projection is in D, and this is a symplectic vectors bundle, and since it is a symplectic vectors bundle, the complement, the symplectic complement is the symplectic complement. And so we have this decomposition. This is the question 15. This is a symplectic decomposition. This is symplectic and this is symplectic. And so we can define one of the properties of this decomposition is that if we consider the Hamiltonian vector field for the free Hamiltonian without constraints, and we apply this projection P, we obtain the non-holonomic dynamics. So this is the first important property of this decomposition. And the other interesting thing is that this permits to define a bracket on M, and this is defined in this equation 16. So we take two functions f and g defined on M. We take the corresponding Hamiltonian vector fields of any arbitrary extensions of f and g on T star Q. We project by the projector P, and we apply the canonical symplectic form, and we restrict to M. So this is a bracket. Of course, this bracket does not satisfy in general the Jacobi property, but satisfy the rest of the properties and provides the evolution of any observable as in the canonical case. So we have two brackets. One bracket on M, on the constraint manifold M. Another bracket on the dual of the non-holonomic vectors subbundle. And nobody knows if these brackets are the same or are related in some way. Well, and the two brackets are called non-holonomic brackets, but nobody proved that they are essentially the same. Well, we prove it in this paper that these are the same modulo and isomorphisms of brackets of But we have another bracket that we can define using this construction by Eden. And this construction is very simple. And this is more simple of this, the constructions. We have this projector gamma from T star Q into M. So we take two functions f and g on M. And we stand by gamma, because composing with gamma, we have functions on T star Q. And we perform the canonical Poisson bracket of these two extensions and restrict to M. So this is the Eden bracket. This is another non-holonomic bracket. And we prove these two results. And this is my final slides. From M to the dual of D, to D star, we can define an isomorphism, a vector bundle isomorphism, just with the inclusion of M in T star Q and the projection on D star using just these inclusions and projections. Well, this isomorphism is an isomorphism between the corresponding non-holonomic brackets. So essentially, the bracket defined using the tangent bundle approach and the bracket using the skew-symmetric Lie algebraic approach are the same, essentially. And the other result that we proved is that the non-holonomic bracket on M is just the Eden bracket. So these three brackets are essentially the same bracket, and this was known now in the literature. Indeed, this Eden bracket is new because we defined the bracket in this way, so it's not defined in this in the original papers by Eden. And so, because well, in his paper, Eden writes the dynamics in a very local way, and so it's not so easy to understand what is doing. Now the further work, part of this work is just completed, is we obtained it using this approach and application to the Hamilton-Jacobi theory, because there were two approaches to Hamilton-Jacobi equation for non-holonomic mechanical systems, and we using some ideas in the paper of Eden, we obtained a generalization of the Hamilton-Jacobi equation for non-holonomic mechanical systems. We have extended this theory for contact Hamiltonian systems, just using similar tools, similar approach by Eden. And now we are preparing a paper just developing this quantization of non-holonomic mechanical systems, just to I think we understand more or less the ideas of Eden. So I think that there is a standard version of our paper in GCI in archive, and you can find all the proofs, because the proofs are not so trivial, so we had to write some pages just to include the proofs. And so, well, this is all, and thank you very much for the attention.
Any comment or question? I have a curiosity. What does it mean, the quantization of a non-holonomic system?
Well, this is an interesting question. So the idea is to quantize, you need a bracket. If you want to follow the ideas of Dirac, this corresponding principle. So you have a bracket given the evolution of an observable. So you have to associate to an observable an operator. And so the operator is on some space of Hilbert space that you have to consider. And so you have to decompose or to pass. Not all the operators will be admissible, because not all the states are admissible in the non-holonomic mechanical system. You have to define something in this Hilbert space just to have a constraint for that avoid that you can use all the possible operators. And so, well, we are working in this idea. Now the thing is interesting because, well, someone can ask, well, what is the interest to quantize these non-Coulombic mechanical systems? But the point is that there are some experiments about nanoballs moving on a graphene surface, and so the quantum effects are present in this potential experiment, because the quantization rules exclude some positions. You cannot move the ball as you want, because the quantum mechanics. So you have to do is this. And so this is, I think, this is a relevant thing just to us in this to develop this quantization approach for non-Holonomic mechanical systems.
You say nanoballs?
Yeah, nanoballs, a very small ball rolling on a.
Nanoballs. Okay.
Yeah. And in the classical picture, the ball can.
Yeah, okay.
But in a quantum picture, so the ball has to cannot, for instance, the angles of are given by the Pauli rules and all these things. So.
Okay. So actually, I have a question. I understand the problem of quantization of non-holonomic systems, but is there has anything been done on the pre-quantization of non-holonomic systems?
Not as I am. Well, one idea could be, because for the pre-quantization, you have, of course, you don't have a symplectic form, so you have to construct this pre-quantization bundle, but you don't have a.
So like on the cotangent.
Yes, yes, but one thing was, and this was one idea. I thought, well, one can consider some kind of non-holonomic mechanical systems. For instance, Chaplin systems, because for Chaplin systems, the group permits that you can reduce the system, the non-holonomic system, to a system with an external force, or even in some cases, this external force vanishes, and you have a real Hamiltonian system. So, an idea as well, what to quantize this reduced Chaplin system and try to recover the.
The Hamiltonization of
Yes, in some sense. So this is more even is more simple, because in Chaplin systems you can prove that due to because the configuration space is a principal bundle over the manifold, and so you can use this to reduce the Lagrangian or the Hamiltonian, if you want, to another tangent bundle on the Q over G, over G is the Lie group, and in this case you have the curvature and the connection given the constraints defines an external force, which is a kind of gyroscopic force. In some cases, if the curvature and the constraints are in some sense orthogonal, this vanishes. So you have a Hamiltonian system. So this was one idea. And the other idea is just to consider not other kind of this twisted non-holonomic mechanical systems, that the bracket of the Nonholonomic you have the product of this the lambdas, the almost Poisson brackets. So this is not zero, but is controlled by a free form. So
any other question or comment? So let's thank the speaker again.
okay, thank you.